In case you're wondering, no, it's not a clickbait title. This video is long and boring. So, are you ready for it? You might just learn something. At the very least, I can say you might learn from this video that it's okay to make mistakes if you don't already know that. And don't be afraid to admit when you do, because I made a couple of doozies on here. Not going to tell you what they are just now. But if you get far enough into the video, I will tell you about one of the mistakes just before I make it. I'm recording this just to edit in and put that in there. So that way, hopefully, nobody will mislearn because of my mistake. So I did want to warn that the mistake is coming up. And I won't say what it is just now. And at the very end of the video, I'll tell you about another mistake in case you missed it. So that video is right near, that mistake is right near the end. So if you get near the end, please watch the last little bit of it, just to make sure that you don't end up thinking that I didn't make a mistake where I did. Welcome. The binary number system is so easy, it's boring. Well, it's a matter of opinion. It can be boring because it's made out of a lot of ones and zeros. I mean, seriously, literally, 0 and 1. That's it. That's all there is. 0 and 1. Nothing more. There is no 2, 3, 4, 5, 6, 7, 8, 9 as far as the digits go. Now, that doesn't mean you can't build higher numbers. Of course, you don't just stop counting at 1 and go, well, that's it, I'm done. I ran out of numbers, can't count any higher. No, in binary, you count with zeros and ones. Just like in decimal, you count with zeros, 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s, and 9s. So let's see, if I make a little room on my screen here. And just clear all this out of the way. Now, here we have two numbers, 0 and 4. If I want to put something in between them, if I want a number that's in between these two numbers, the easiest way to do that, of course, is pick a number exactly halfway in between them. So it's halfway between 0 and 4. Now, I'm not using binary right now because notice there's a 4 there. I'm using decimal, ordinary number system. So what is between 0 and 4? Halfway between 0 and 4. Well, of course, half of 4 is. That would be 2. So what if I want to put something in between 0 and 2? Again, the easiest way is to go halfway between them, which is 1. Well, easy so far, but what if I want to put something between 2 and 4? Well, again, it's gonna be, the easiest one is going to be halfway in between them. And in this case, that's the number 3. Now, so far, this is pretty easy, right? What happens when I want to put something between 0 and 1? Well, now, if you haven't learned fractions or decimals yet, you might have a problem there. But let's just say we decide to go with fractions. So we'll call that number 1/2, which is half of 1. Okay, that's easy enough. What if I want a number halfway between 1 and 2? Well, that's going to be 1.5. What if I want a number halfway between 2 and 3? Well, that's going to be 2.5. Notice a pattern here. What if I want a number halfway between 3 and 4? Well, again, that's going to be 3.5. So what if I want to put a number between 0 and 1/2? What would be halfway between those two? Well, this is where it starts to get a little bit complicated. If you're if you're an adult and you know math, normal adult level, you probably already know the answer. If you're a kid watching this who hasn't gotten to fractions yet at all, this might be a little confusing at first, but don't worry about it. We have 1/2, which is a 1 over 2, meaning 1 part out of 2 as the number between 0 and 1. Well, 2 plus 2 is 4. So if I want half of 2, I want to divide by 2 again. In other words, 1/2 part of 1/2. So 1/4. And what if I want a number halfway between 1/2 and 1? That would be 3/4. Now, 1/2 is also equal to 2/4. So, in a sense, we're just counting here. We go 0, 1/4, 2/4, 3/4. 1 would be 4/4. In between 1 and 1.5 would be 5/4, or 1 and 1/4. 5/4 is 4/4, which is 1 plus 1/4. In between 1.5 and 2, well, 1.5 is 1 and 2/4. So we want 1 and 3/4. Halfway between 2 and 2.5, well, 2 is 8/4, or 1 and 4/4. So we're going to want 2 and 1/4, or in other words, 9/4. In between 10/4 and 12/4, or in other words, in between 2.5 and 3, we're going to have 2 and 3/4. That's 8 and 4/4, or 12/4. Wait, did I say that right? No, sorry. 8 and 3/4. 11/4. Yeah. I'm not perfect. None of us are. I made a mistake. But when you make a mistake, don't forget it's okay to call yourself out on it. It's okay for someone else to call you out on it. It's all right to be wrong. But it's important to recognize when you're wrong and make the correction if you can. Because if you can't accept the fact that you're wrong, then you'll never recognize when you have something that you need to relearn or learn correctly or learn to do better, because you'll never know that you were wrong. You got to be able to recognize that. So moving on, what would be between 3 and 3.5? Well, of course, there are a bunch of numbers between there. But what's directly halfway between 3 and 3.5? Well, that's going to be 3 and 1/4. And halfway between 3.5 and 4, that would be 3 and 3/4. Now notice all of those fractions that I've just added have a 4 in the denominator. The ones I did in the last time across between 0 and 4 had a 2 in the denominator. And technically, the ones before that had a 1 in the denominator. That would be the 1 and the 3, which is 1 over 1 and 3 over 1. And the one before that, halfway between 2 and 4, technically kind of had a 1/2 in the denominator. Now that might not be real obvious, but if you write a fraction of 1 over 1/2, or in other words, 1 divided by 1/2, then that would be the reciprocal of 1/2. Anytime you divide 1 by something, you get the reciprocal of that thing. Well, the reciprocal of 1/2 is 2 over 1, which is 2. So, moving on. What do you expect to be in the denominator if I try to put a number between 0 and 1/4? Halfway between again. Well, so far we've got in the denominator we go 1, 2, 4. What's next? Well, you might think 2, 4, 6, 8, even numbers, right? But 1 isn't an even number. So that's not the pattern we're looking at here. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. The answer is 1/8. 8 is in the denominator. What's between 1/4 and 1/2? Halfway between 1/4 and 1/2 is 3/8. Halfway between 1/2 and 3/4, 5/8. Halfway between 3/4 and 1, 7/8. Halfway between 1 and 1 1/4, that's 1 and 1/8. Between 1 1/4 and 1 1/2, halfway between is 1 and 3/8. Halfway between 1 1/2 and 1 3/4, 1 and 5/8. Halfway between 1 3/4 and 2, that would be 1 and 7/8. Halfway between 2 and 2 1/4, that would be 2 and 1/8. See a pattern here? Halfway between 2 1/4 and 2 1/2 is 2 and 3/8. Now you might wonder why I'm showing you all these fractions in decimal when we're here to talk about binary. Well, binary is base 2. And notice we multiply 1 by 2 to get the 2 that goes in the first denominator, and multiply that 2 by 2 to get the 4 that goes in the second set of denominators, and multiply that 4 by 2 to get the 8 that goes in this set of denominators. So again, in the next set of denominators, what are you going to expect is going to come next? In between 0 and 1/8. What's half of 1/8? It's 1/16. Halfway between 1/8 and 1/4, 3/16. Halfway between 1/4 and 3/8, 5/16. Now notice, this is really not that hard. 7/16, 9/16, 11/16, 13/16, 15/16, 1 and 1/16, or 1 and 1/16, or another way of looking at it, 7/16. Between 1 and 1/8 and 1 1/4 would be did I say that wrong? 1 and 1/16 is the same as 17/16. Between 1 and 1/8 and 1 1/4 would be 19/16, or in other words, 1 and 3/16. We keep going. 1 and 5/16, 1 and 7/16, 1 and 9/16, 1 and 11/16, 1 and 13/16, 1 and 15/16, 2 and 1/16, 2 and 3/16, 2 and 5/16, 2 and 7/16, 2 and 9/16, 2 and 11/16, 2 and 13/16, 2 and 15/16, 3 and 1/16. So if I follow that pattern all the way to the end, here's the last one between 3 and 7/8 and 4. Halfway between those two is 3 and 15/16. And notice, add one more 16th to that, and we have 4. If we wanted to continue this pattern, the next fraction would have 32 in the denominator. But we're not going to do that because, well, decimal can be boring too. Fractions can be boring. Anything's boring if you do too much of it. So let's move on. Let's just say, scroll this. Yeah, I think I went off the screen there. So, getting ahead of myself. Okay, we have again 0 and 4. And if I want to go in between the 0 and 4, halfway between is the number 2. If I want halfway between the 1 and the 2, it's the number 1. Halfway between the 2 and the 4 is the number 3. Now, we went over this last time, but now I'm going to do something different. Halfway between 0 and 1, instead of saying 1/2, we're going to call this 0.5. Now notice the 1 is in the ones place in the number 1. The 0 is in the ones place in the number 0. The 5 is not in the ones place. It's in the 1/10ths place. A fraction of 10, or a fraction, 5 parts out of 10. Well, 5 parts out of 10, 5 is half of 10. So that's 1/2. And over here, we're going to have 15 parts out of 10, halfway between 1, which is 10 parts out of 10, and 2, which is 20 parts out of 10. So 1.5. Halfway between 2 and 3, 2.5. Halfway between 3 and 4, 4.5. Now, this looked pretty easy again, doesn't it? But does it stay that way? What comes in between 0 and 0.5? Well, this time, we're not going to be just sticking a digit on the end. In between 0 and 0.5 is 0.25. It's kind of like saying the 5 represents 5 in the 10ths place and 0 in the 100ths place. 5 0 is 50, half of 50 is 25, so we want 25 100ths, which is half of 50 100ths. In between 50 100ths and 100 100ths, halfway between is 75 100ths. So halfway between 0.5 and 1 is 0.75. Halfway between 1 and 1.5 is 1.25. Now you might notice this is getting a little bit more thought intensive here. If we really want to work this out, it's not a terribly difficult task, but at least it's not boring, right? Because there's something to figure out. So this is kind of what I mean about binary being so simple, it's boring. Because what is there to figure out? Well, we'll get to that. Let's go ahead and continue this pattern here. 1.75, 2.25, 2.75, 3.25, 3.75. Now notice these are all 2 digits after the decimal point. And when I get to between 0 and 0.25, will I have a 3rd digit after the decimal point now? Sure enough, we got 0.125. So between 0.25 and 0.5, 3 digits again. Sure enough, 3.75. What about between 0.5 and 0.75? Yep, 0.625. What about between 0.75 and 1? 0.875. What about between 1 and 1.25? That would be 1.125. Now notice we had the 0.125 up there, and the one we added after that, after the 0.25, was the 0.375. So in between 1.25 and 1.5, we get 1.375. So there's a pattern here again, like there was with the fractions. Each time in between these numbers, we're literally adding another 0.25 each time. Or is it 0.25? Did I say that wrong? I might have said that wrong. We're adding another, yeah. Is it 0.25? Oh, yeah, we're adding 0.25 to... Well, we're adding 0.125 to the number that we're coming after. Yeah, you know what? 0.25. That's right. I said that right the first time. I have no idea why it threw me off. 0.25. Okay, let's do this. Here. This one we just put in is 1.375. Okay, after 1.5 will be 1.5 plus 1.5 plus 0.125, which is 1.625. Add the 0.1 to the 0.5 and you get 6, and then the 25 from the 0.125 is being added to 0. So that'll be 0.625. But if we look back at the 1.375, and we do it that way, then we're adding 0.25 to that to get to this position. Well, 0.25 added to 1.375, the 1 stays where it is. The 0.2 gets added to the 0.3. That gives us 0.5. 3 plus 2 is 5. The 7 gets the 5 from 0.25 added to it. Well, 5 and 7 is 12. So we're going to be carrying 1 then. So the 1 carries over to the 5 in the 1/10th place, and we end up with 6 there. So we'll end up with 0.625. Same answer, different way of coming about it. Between 1.75 and 2 is 0.1875. And so on, 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 until we've run out of this row of inserts, and now we're back to the beginning. So what should I expect to get between 0 and 0.125? Some people might already know the answer, but just think about this. We had no digits after the decimal, and then 1 digit after the decimal, and then 2 digits after the decimal, and then 3 digits after the decimal. Should we be getting 4 digits after the decimal here? There it is, 0.0625. Now, can you be sure this pattern is going to hold? Here we got 0.1875, and here we get 0.3125. Now that's getting just a little bit on the complicated side, isn't it? So we're adding 1/8, 1/16 each time now. We're back to adding our 1/16 like we did with the fractions. And I'm just going to go ahead and fill this row out. And hold on, it scrolled off the screen. Let me bring that back on. And you can see each one. Again, we're just taking the number out of the two numbers that we're trying to get one halfway in between, since those are 1/8 apart, and we're just adding 1/16 to the first one. Or we can subtract 1/16 from the second one, either way, and that gives us our number that's halfway in between them. But notice, it's hard enough to do that in fractions. And the smaller the fraction, the more times you want to go halfway in between, the harder it's going to be. And what if you have some arbitrary set of numbers like 37 and 156.125, and you want to go halfway in between those? Well, then you're getting a little more complex, and you might want to pull out a calculator and just add the two numbers together and divide by 2, which will work. But let's just go ahead and fill this out, and then we're going to get onto the binary here. Here's 3.8125, and the last one we're inserting between 3.875 and 4 is going to be 3.9375. So, scrolling this up out of the way, and let's put this on the screen. Now, why that? Why 0 and 100 this time instead of 0 and 4 like we did the other 2 times? Well, the answer is this isn't 0 and 100, because now we're in base 2, binary. 100 represents a 1 in the 4's place, a 0 in the 2's place, and a 0 in the 1's place. So this is a binary representation of 4. In binary, you would count 1, 1 0, 1 1, 1 0 0. 1 0 0 is your 4th number. So what is going to go halfway in between 0 and 100. Well, again, you count 1, 10, 11, 100. So 1, 10, 11, 100. Inserting here from 0, 1, 10, 11, 100. But that's your whole numbers. What happens when you want to go halfway in between 0 and 1? Well, I did say binary was easy. 0.1. Stick a 0.1 on after your 0. How about between 1 and 10? Again, take your 1, put a 0.1 on the end. What about between 10 and 11? Well, you take your 10 and you put 0.1 on the end. What about between 11 and 100? Take your 11, put a 0.1 on the end. So all we're really doing is we're adding in a 1 in the 1/2's place on each one of these. And adding that 1 in the 1/2's place is really easy to do because the 1/2's place had 0 in it. So you're adding something to 0. And adding to 0, of course, is real easy because whenever you add something to 0, you'll get the something that you added to 0. So what about here? Between 0 and 0.1. Well, again, 0.1 in binary is 1/2. So half of 1/2 is 1/4. So we want a 1 in the 1/4's place. Or in other words, in the place value of 2 to the negative second power. Well, 2 to the second power is 4, so 2 to the negative second power is 1/4. So that. Well, I hate to interrupt myself to point out that I'm about to make a really big mistake, but I'm leaving it in. So I need to tell you what it is. I'm about to misuse the phrase, the term decimal point, when what I really mean is binary point. So let me explain that. When making decimal fraction numbers using a decimal point, we might write, for example, 1.5 to mean 1 and 5/10, or 1.05 to mean 1 and 5/100. That's using the decimal system, so the point is a decimal point. Now, you can use the same point in binary, and yes, it often gets called a decimal point, but that's technically incorrect because decimal is base 10. It's a binary point, and I make that mistake coming right up here multiple times before I catch myself at it. So when I catch myself at it, I will point it out. But I wanted to point it out in advance in case anybody doesn't quite watch far enough to catch me catching myself. So at least you don't end up walking away slightly misinformed. The binary point, when you put, for example, 1.1, that means 1 and 1/2. 1.01 is 1 and 1/4, or in other words, 1 and 1/2 of 1/2. 1.001 is 1 and 1/2 of 1/2 of 1/2, or in other words, 1 and 1/8. So it's really not correct to call it a decimal point. Again, it's common. Be ready for that out there. Yeah. Back to the instructions. Thanks for hearing me out. So that's going to be our second digit, 2 to the negative second power, therefore our second digit after the decimal point. 1/2 was the first digit after the decimal point. That's 2 to the negative first power. 1/4 is going to be the second digit after the decimal point. So 0.01. Again, we're just taking our 0, or 0.01, 0.0000000, however many zeros you want to throw on the end, because they won't change it. And we're adding 0.01 to that. We're adding a 1 in that second digit after the decimal point. So what's going to go between 0.1 and 1? Well, again, take your 0.1 and add a 1 in the second decimal place after it. What's between 1 and 1.11? Well, halfway between, what's halfway between 1 and 1.1? Well, halfway between 1.1 is 1.01. Halfway between 1.1 and 10 is 1.11. Halfway between 10 and 10.1 is 10.01. Halfway between 10.1 and 11 is 1.11. This is really not hard math. Halfway between 11 and 11.1 is 11.01. Now, notice all I'm doing is I'm taking my 11, I'm putting a 0.0 after it so that the next digit I'm adding on is in the correct place value, the 1/4 place, or the second digit after the decimal, and then I stick my 1 in there. 1.1 already has one digit after the decimal, so I don't have to add that in. I just put 1.1, and add another 1 after it. So what about back here between 0 and 0.01? Is that any trickier? It got trickier with the decimal when we started dividing, when we started adding in quarters and eighths and sixteenths. Well, we just added the quarters. Let's have a look at 1/8. It's 0.00. Can you guess it? 1. That's your 1/8 place. So if I want to add the 1/8 place to the next number, to 0.01, all I'm going to do is take my 0.01 and put a 1 on the end of it. So how do I do that with 0.1? Well, again, it's got to go in the third place. That's your 1/8 place. So we'll take our 0.1, add a 0 at the end of it to fill up that second place, and then put a 1 in the third place after the decimal. So 0.101. How about halfway between 0.11 and 1? Again, 0.11, and add 1 in our 8th place. So literally what this number is saying is 0 in the ones place, 1 in the halves place, 1 in the quarters place, and 1 in the eighths place. In other words, 1/2 plus 1/4 plus 1/8. Well, 1/4 is 2/8, and 1/2 is 4/8. So 4/8 plus 2/8 plus 1/8 is 7/8. And notice there are no more eighths left to add before we get to 1. How about between 1 and 1.01? Well, again, 1.01 in binary is actually 1 1/4, so this is going to be 1 1/8. Take our 1, put 2 zeros after it, and in that third digit after the decimal, put in a 1. That's our 1/8. We want to add 1/8 to 1.01, stick a 1 after it. We want to add 1/8 to 1.1, fill up the second place after the decimal with a 0, stick a 1 after it. We want to add 1/8 to 1.11, already 2 digits filled after the decimal, so put a 1 after it. A 1 0, remember, that's a 1 in the twos place, and a 0 in the ones place, so that's our number 2. What's halfway between 2 and 2 1/4? Well, 2 1/8. So we take our 2, put 2 zeros after the decimal to fill up the halves place and the quarters place, and then stick a 1 after it to add 1/8. Halfway between 10.01 and 10.1, take our 10.01, put a 1 after it. That adds 1/8. Halfway between 10.1 and 10.11, take our 10.1, fill in a 0 in that second decimal, second place after. Why am I calling this a decimal point? It's a binary point. Seriously. Now, I didn't even catch myself doing that this whole time, and I should not have been doing that. I should go back and edit this thing and fix that. But you know what? I'm not going to. I'm going to leave my error in there. I hope anybody watching this doesn't stop just before I caught myself in that error. I'll tell you what. If you're watching this and you got to the point where I caught myself in that error, since I'm being nice enough to leave my error in there, please share this video. And I did not do this on purpose just to be able to say this, but please share this video, point out my error, or ask other people to watch it and just tell them I've got an error in there and tell them to watch it and see if they can catch it. And they'll find out I caught myself. All right. So, binary point, not decimal point. Yes, it's a point. It's not a decimal point when we're working in binary, because decimal point means that we're using decimal. Wow. I messed that up badly. Okay, so halfway between 10.1 and 10.11 is going to be 10.101. And halfway between 10.11 and 11, notice 10.11, all of our decimal places are both our first and second. I did it again. Both our first and second places after the binary point are 1s. So I can't add another 0.01 to that without turning that over. And that's how, when we added that 0.01 earlier, when we were adding the 0.01, that's how that one ends up. The next step is the 1, because we turn over that digit if we add 0.01. But if we're adding 0.001, then all we have to do is take that number and stick a 1 on the end of it. 0.001, we're adding 0 to 1, 0 to 1, and 1 to 0. 0 plus 1 is 1, 0 plus 1 is 1, and 1 plus 0 is 1. So we get 10.111. Now I need to scroll this thing so it's not off the screen. Oh, I scrolled it the wrong way. Here we go. So in between the 1, halfway in between 1 and 11.01, I wonder if I should insert a piece of something. I think I will insert something. I'm not going to edit out my error, but I think I'll record a little piece and try to insert it in there if I can, before I make the error, to warn anybody who might stop the video before then that I'm making a mistake there. Calling it a decimal point, it's like a colloquial usage. I mean, we're so used to calling things certain things, we just do that. And I messed up that one badly. At any rate, okay, so halfway between 1 and 11.01. Basically, here's what we're doing, if this makes any sense. Halfway between 11.00 and 11.01, I'm going to take the difference between them, which is the 0.01, and divide that by 2. Well, half of 0.01 is 0.001. And then I add that to the 0.11 and I get, or to the 11, and I get 11.001. So that's why it becomes 11.001. That's actually where that's coming from. The 1/4 as 0.01. When you divide it by 2, you just shift it to the right one. In fact, in binary, you can divide any number by 2 by simply moving your binary point one position to the left. That's it. That's how you divide something in half in binaries, is you move your binary point one to the left. And if you want to multiply it by 2, you move your binary point one to the right. If there's no digits after the binary point to move it to the right of, well, then you stick a 0 after the binary point and you move your binary point after that 0. And that's multiplying by 2, or multiplying by binary 1, 0. That's doubling your number. So between 11.01 and 11.1, we get 11.011. And between 11.1, also known as 11.10, and 11.11, we get 11.101. And between, wait, did I say, I'm not sure if I messed up and said I was adding a 16th somewhere along the way in here. I might have. Yeah. There again, errors happen. I hope you learned something from this anyway, and I hope that I've made this video somewhat entertaining, if nothing else, by humiliating myself terribly. Okay, halfway between 11.11 and 100, again, we're going to add an eighth, which is 0.001, to the 11.00, or sorry, to the 11.11. So 11.11 plus 0.001 is 11.111. Now, what's halfway between 0 and 0.001? Well, remember what I said? To divide anything in half in binary, just move the binary point 1 to the left. So what is, if I take that 0.001 and I move the binary point 1 to the left, that's going to put it in front of that first 0. So I'm going to get 0.0001. And if we write that out as 0.000, then 0.0001 becomes 0.0001. The 0 before the decimal point doesn't change the value any more than another 0 after that last 1 would. Those are just placeholders that don't really change the value at all. Now, zeros that get in the way of between other digits and the binary point, they make a difference. If you squeeze a 0 in between the binary point and anything after it, you divide that stuff after it by 2. And if you squeeze a 0 in between the binary point and anything before it, that stuff before it gets multiplied by 2. So what's between 0.001 and 0.01? Well, that's going to be 0.0011. And between 0.01 and 0.011 is going to be 0.0101. And between 0.11 and 0.1 is 0.111. Between 0.1 and 0.101 is 0.100. 1. Between 0.101 and 0.11 is 0.101, 1. Between 0.11 and 0.111 is 0.110, 1. Again, all I'm doing is adding a 1 in that fourth binary place, not decimal place. That's the hardest thing really about learning a new number system, is getting the terminology down. And when it comes to binary is so simple that getting the terminology down and breaking old habits is by far the hardest part, because there's really nothing hard about binary. Converting it into decimal and back, that can be a little bit hard, but even that's hard because of decimal, not because of binary. So what's between 0.0111 and 1? Well, that's 0.0111, 1. So there we've ran out of digits. We've ran out of room to add 0.0001 before we end up with 1. So we add 0.000. We add 0.0001 to 0.1111. We get 1. And when we add 0.0001 to 1, we get 1.0001. And when we add 0.0001 to 1.001, we get 1.0011. So that's the whole pattern. Take that number, put a 1 on the end. Take that number, put a 1 on the end. Take that number, put a 1 on the end. We just have to make sure we've got 4 digits, got 3 digits already after the binary point before we throw that 1 on, and that 1 in that fourth digit is our 1/16 that we're adding, our 2 to the negative fourth power. And there we've got 1.1111. And here we're going to put in 10.0001. And here we're going to put in 10.0011. And here we're going to put in 10.0101. And here we're going to put in 10.0111. Here, 10.1001. So really, I'm just going to go ahead and zip through these and just put them in, because I'm probably boring my viewers if there's anybody still watching at this point. Like I said, binary is so simple, it's boring. Okay, here we are with 11.001. Put a 1 on the end. 11.01, add a 0 to make it long enough, and then put a 1 on the end. 10.11, add a 0 to make it long enough, and oh wait, it was long enough. 11.011. Confusing myself for no reason. This is the one I was thinking of. 1.1. Add 2 zeros on the end to make it long enough, and then put a 1 on the end. So that's all we're doing. Stick a 1 on the end, or stick a 1 in the fourth binary place. Or binary fraction place, if I want to be real technical with the terminology. With decimal, we never do that. We say decimal place. Technically, what we mean is decimal fraction place. The second decimal fraction place is the 1/100th place. The third decimal fraction place is the 1/1000th place. The first decimal fraction place is the 1/10th place. But we call that the first decimal place because it's shorter and we generally don't think much about it. And maybe we should. Maybe when we're teaching kids decimals, we should, be specific about that. when teaching decimal fractions that it's a fraction place, not just a place. It's not a decimal place. 1 is the first decimal place. A 1 in the number 10 is technically the second decimal place, the second place in the decimal system, but those are places before the decimal point and not after. So, yeah, I don't want to confuse anybody with the terminology, just pointing out that it's already confusing all on its own. So, what do we get when we add 0.0001 to 11.0? Oh, sorry, to 11.111. Well, 0.0001 has zeros in all three of those binary fraction places that this one has ones in. So those are going to stay 1, and our 1 at the end of 0.0001 will get tacked on to make 11.1111. So, I hope you found this interesting. Now, how would you like me to, well, you can't answer the question, I won't hear you, but how would you like me to show you an entire multiplication table in binary? Or is that a little too hard? Maybe I should start with an addition table. To do both, let's just do that. Clear the screen and let's just do all of our one-digit multiplications or one-digit additions in binary. 0 plus 0 equals 0. 0 plus 1 equals 1. 1 plus 0 equals 1. 1 plus 1 equals 2. Well, technically, yeah, you could do that. There is no 2 in binary, no 2 needed. You could put it there, but it'll throw off most people who know binary because they're not going to be expecting to see a 2 in binary, because that 2 actually represents in binary 1, 0. 1 in the 2's place, 0 in the 1's place. I can do the same thing in decimal. I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, where A is representing 10, B is representing 11, C is representing 12, and then I can say 9 plus 2 equals B. B, of course, representing 11. So that can be done in decimal as well. As a matter of fact, if I want to do that in binary, I could say F plus 1 equals 1, 0, 0, 0, 0. How is that? Well, that's because F equals 1, 1, 1, 1. If we go through that same method of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. 0 in binary is, if we want to write it as 4 digits, 0, 0, 0, 0. 1 is 0, 0, 0, 1. 2 is 0, 0, 1, 0. 3 is 0, 0, 1, 1. 4 is 0, 1, 0, 0. 5 is 0, 1, 0, 1. 6 is 0, 1, 1, 0. 7 is 0, 1, 1, 1. 8 is 1. Oops. 1, 0, 0, 0. There's our 8. 1, 0, 0, 0. Now notice that's just like 0, but with 1 added in the 8th place. Our 9 is 1, 0, 0, 1. That's just like 1, but with 1 added in the 8th place. Our number after 9 is 1 in the 8th place and 0, 1, 0. Our number after that is going to be 1 in the 8th place and 0, 1, 1. And our 1 and our next, our 12, if we want to call it that, or C in this system, is going to be 1, 1, 0, 0. And the next digit after that is going to be the D represents, in this case, 1, 1, 0, 1. And the E represents 1, 1, 1, 0. And the F represents 1, 1, 1, 1, as I mentioned earlier. Now, that 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, if you've ever heard of hexadecimal, that's where that comes from. Every binary digit, every hexadecimal digit directly translates into 4 binary digits. And here's the order they're in right here. So binary 0000 is hexadecimal 1. Binary 0001 is, 0000 is hexadecimal 0. 0001 is hexadecimal 1. 0010 is hexadecimal 2, and so on. At any rate, we did all our additions up here. 0 plus 0, 0 plus 1, 1 plus 0, and 1 plus 1. Now notice only one of those actually ended up with a carry, the 1 plus 1. And these other ones, we can write them as 0, 0, 0, 1, and 1, 1 if we choose to. Same thing. So if we want to do these in 4-digit groups, like our hexadecimal numbers, we could say 0, 0, 0, 0 plus 0, 0, 0, 0 equals 0, 0, 0, 0. And we could say 0, 0, 0, 0 plus 0, 0, 0, 1 equals 0, 0, 0, 1. And we could say 0, 0, 0, 1 plus 0, 0, 0, 0 equals 0, 0, 0, 1. And 0, 0, 0, 1 plus 0, 0, 0, 1 equals 0, 0, 1, 0. So if we do it that way, if you think of those 4-digit groups as hexadecimal, in a sense, there's no carry anymore. We just changed to a different hexadecimal digit. In this case, the hexadecimal digit represented by the binary 0010, or 2. 1 plus 1 equals 2. In this case, 1 plus 1 equals 10. So let's try multiplication now. Let's just change the sign here and say 0 times 0. Well, that equals 0. We know that. 0 times 1 also equals 0. 1 times 0 also equals 0. And 1 times 1, well, that's going to equal 1. Let's just move this down here and take these extra zeros out of the way. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. And 1 times 1 is 1. Matter of fact, that's really all the one-digit multiplications you have in binary. Multiplying by 0 and multiplying by 1. Anytime you multiply by 0, you're going to get 0. And anytime you multiply by 1, you get the number that you're multiplying by. So you don't really even need your multiplication. You don't really need multiplication tables because it all comes down to addition. I promised I was going to point out another mistake I made right near the end there. I said change the sign when what I meant was change the operator. Now, yes, plus is used as a sign, and I was changing the plus, but I was changing it to an asterisk to represent multiplication, one of several ways that multiplication gets represented in mathematics. And so it was a mistake to say change the sign because I wasn't changing a sign. Even if I was changing it from plus to minus, since I was doing addition, changing it from addition to subtraction would still be changing an operator, not changing a sign, because plus isn't a sign in that context, it's an operator. So, yeah, my mistake. And one more mistake right near the end that I think is worth pointing out. If I can word it, if I can quote myself as well as possible, I basically said that when you multiply by 1, you always get what you're multiplying by. Now, what I meant to say was when you multiply by 1, you get what you're multiplying 1 by. Because when you multiply by 0, you get what you're multiplying by, which is 0. But technically, when you multiply one thing by the other, you're also multiplying the other by the one thing. And so, yeah, it's iffy. It's just poor wording. I should have worded it better. What I meant to say was when you multiply by 1, you always get what you multiplied. So, in other words, if you multiply, for example, 7 times 1, you'll get 7. Multiply 145 times 1, you'll get 145. Multiply the square root of negative 2 by 1, you'll get the square root of negative 2. And my point being that in binary, all of your multiplication is always multiplying by 0, multiplying by 1, and moving the decimal point. That's really all it is. And then, of course, the addition of those parts. So, for example, to multiply by 17 in binary is 10001. The first 1 in that is multiplying by 16, which is done by just adding 4 zeros to the end of whatever you're multiplying. The other one is just 1 times whatever you're multiplying, so just the number. So, for example, if the number you're multiplying is 111, then 17 times that, or 10001 times 111 is going to be 111,0000 plus 111. Which comes to 111,0111. I can do it in my head. Really not that hard. Now, if I convert it to decimal, okay, you might not even believe this happened, but I have to edit to stop myself in the middle of correcting an error, to correct an error I was making while correcting the error. Yeah, okay. I multiplied 111 times 10001, and I got 111,00011. Oh, no, sorry. Got 111,0111, which is correct in the binary. And then I went to convert it into decimal, and I actually got the wrong binary numbers. I forgot which one of the numbers I used. I don't know, forgot exactly, but yeah, the wrong one. So okay, let's do this right. 1110111 was the result of multiplying 10001 times 111. Okay, 10001 is 17. 111 is 7. 1110111 is 64 plus 32 plus 16, which is 112, plus 4 plus 2 plus 1, which is 7. 112 plus 7 is 119. 17 times 7, also 119. What I mistakenly did is I went to 101 instead of 111, replaced the 7 with a 5. So binary 10001 times binary 101 is 1010101. 1010101, yeah, 1010101. A little repetitive. How that works is 101 is 4 plus 1. 4 plus no 2's plus 1. So that's 5. The 101 times the 1 in the ones place of 10001 is just 101. 101 times 1 is 101. In other words, 5 times 1 is 5. The other 101 times the 1 in the 16's place is 101 times 16. 101 being 5, and of course 5 times 101 binary times 16 decimal. 5 decimal times 16 decimal is 80, or another way of looking at it is 101 times 10000, which is the 1 in the 16's place, is 4 times 16 plus 1 times 16, or yeah, 4 times 16 is 64. So 64 plus 16 plus 4 plus 1. 64 plus 16 is 80. 4 plus 1 is 5. 80 plus 5 is 85. So if I work from the binary of the one I mistakenly did, I end up with 85. And now I'll go back and you can hear what I did in the decimal. If I convert it to decimal, 10001 17. 101 is 5. 5 times 17. Well, let's see. One way to do that would be 10 times 17 and then divide it by 2. 10 times 17 is 170. Divide that by 2. I get 50, and 35 is 85. I'm not even certain. I think I did that right. I'm reasonable with math. I'm not great at it. I'm not one of these, human calculators. And binary is a lot easier than decimal. Simple matter of fact. But it is also more boring than decimal. Fortunately, computers don't get bored easily. It's fortunate because binary is what all modern computers do their math in. Now, sure, there were some early computers that actually used base 10 at the core, but our modern computers, they use base 2 internally. Even the older 8-bit like Atari computers running on was a 6502C microprocessor. They had an operation for decimal math built into that 8-bit processor, but it was what was called binary coded decimal arithmetic. Binary coded decimal meaning technically the digits were hexadecimal digits, and they did math on them as if they were decimal digits. So, for example, 20 times A would be 200 because A represented 10. Any rate, yeah, wanted to point out that little sort of trivial error. And there might be more mistakes that I didn't even catch myself making. But yeah, don't be afraid to admit when you make mistakes. Try to catch yourself in them if you can. And if somebody else catches you in a mistake, thank them for it. I do. Thanks for watching.